Hello guys again. Today we are going to be doing Euclidean geometry. So yeah, we are given, so with these types of problems, you're going to have to read the statement properly so that you know what you're given about your problem. And like, Euclidean geometry is hard and it's also easy if you take into account the entirety of the given statement. Well, then you might have your answer. What I'm just trying to say, if you read your given statement carefully, you might find that you've solved the entire question. So then now let's see. Given COD diameter, so you remember all the theorems which are associated with the diameter. So we know the diameter passes through the center, and angle in a semicircle, you're going to have 90 degrees there. And then we're given that EA is a tangent to the circle. So now when we think about EA or the tangent, remember the tan chord theorem, right? So the tan chord theorem, it has to do with the tan and the chord. So you have a tan, and then you have this tangent, and then you have this tangent, then you have this chord, right? So you see that this angle F4 is the angle between the tangent and the chord, and it shall be equals to that angle over there, C2, which is subtended by that same tangent. So what I'm saying is that F4 is equals to C2, right? And then that's another thing, we have another tangent here, another chord here. Yes, so this chord is in contact with this tangent, right? And if it's in contact with this tangent, you see that you have an angle here between them, and this angle F1 will be equals to the angle D1 plus D2, which is subtended by FC. So that means that you have F1 equals to that. And the last thing which we can see is that if you have a radius, because this is from the center, and the tangent, right? The angle which forms between them, that's 90 degrees. That means that we have 90 degrees here. Right. And then we continue. And then we are told that OB produced intersects the tangent to the circle at A, yeah, and then CF intersects OB in T, okay? Then they're given CB, BD, OF, and FD are thrown. So another given statement which we can just put here, we can just say that OB is equals to OC is equals to OD. Why? Because they are all radiuses. Because you have OD is a radius, OC is a radius, and you have OB, which is also a radius like that. And then so now we are going to solve the first question, right? Oh yes, another thing is that, before I forget, is that here you have your diameter. Yes, we did find that it's subtending that one at the circumference. It's going to be 90 degrees, but it's also subtending this angle over here. You see it, right? This angle. So that means we also have a 90 over there. So what I can do here now is that I can do a 90 degrees here. So they are saying that we must prove that TODF is a cyclic quadrilateral. So TODF is a cyclic quad. So now there are only three ways in which you can prove a cyclic quad. So that you have something of this nature, Sorry, forgive my drawing here, it's a bit bad. So you're gonna have something of this nature, right? And then if you prove that this angle is equals to this angle, and then that means that this entire diagram is a cyclic quadrilateral. Or you can have something of this nature, so quadrilateral, and if you prove that these opposite angles, their sum is 180 degrees, or if these two, their sum is 180 degrees, then you prove that this thing is a cyclic quad. And the last one now is if you have something like this. So like if you prove that this angle is equals to this angle, then you have proven that this entire thing is a cyclic quad, right? So let's continue. Let's look at what we have in this situation. We have that let's prove that TODF is a cyclic quadrilateral. TODF is this diagram. So then now what I see, you might find a different way of solving it, but what I see is that already in this TODF we have a 90 degrees here, which we found when we were analyzing our given statement. And then with this 90 degrees again, over here, we have a 90 degrees over there. So as you see that 90 degrees, what we are going to do is that we are going to find that the sum of this and this is 180. And because the sum of these opposite angles is 180, it must show that this TODF is a cyclic quad. But then how do you actually write that, right? So now we are going to say that OT is equals to 180 degrees minus 19. Why? Angles on a straight line. Therefore, DOT is equals 90 degrees. So DOT is this angle over here, this one. It's equals 90 degrees. And then the other one we see it's going to be CFD, right? So we see that CFD is also equals to 90 degrees. But then what do we say about this when you say angle in a semicircle? Yeah, you can write angle in a semicircle, you can write angle in half circle. It's there on the exam guideline. I just find it very cool to do. And then now what you're gonna see is that you're gonna say CFD plus DOT is equals to 90 degrees plus 90 degrees, and this is equals to 180 degrees. So because this is equals to 180 degrees, therefore TODF is a cyclic quad. And the reason being converse opposite angles of a cyclic quad. So when we use it, we say opposite angles of a cyclic quad, but then when we are proving it, we say converse, or when we are proving using it, we say converse opposite angles of a cyclic quad. And then we continue, we say we must prove that angle D3 is equals to T1. So D3 is this angle over here, and then T1 is over here. But what did we just prove? We proved that this is a cyclic quad, right? So if this is a cyclic quad, this must imply that D3 is equals to T3. Why? Because of exterior angle of a cyclic quad, right? Because you can see here it extends like this. So that means that D3 is an exterior angle. It's going to be equals to that opposite interior angles over there. So now what you're gonna say is that for 10.2, D3 is equals to T3. And what's the reason? Exterior angle of a cyclic quad, right? And then you know that your T1 is equals to angle T3. Why? Because of vertical opposite angles. And therefore angle T1 equals to angle D3. Why? Because they are both equals to angle T3. So now we have just proven that one. And this was 10.1. So now we're coming to 10.3. You must prove that triangle TFO is similar to triangle DFE. So we're going to do a rough thing sketch here. So now, well, a rough work to say. So now when you're solving your similarity questions, right, you're already given which angles are going to be equal, because you have triangle TFO similar to triangle DFE. This is what you're supposed to prove, that they're similar. So already based on the structure, you know that T is supposed to be equals to D, and your F is supposed to be equals to your F, and your O is supposed to be equals to your E. So now let's look at our two triangles here. We have DFE and we have TFO. All right. So now what we know about these triangles already is that this D is supposed to be, this T in TFO, T3, is supposed to be equals to the D, right, in TFE. That means that T3 is supposed to be equals to angle T3. And we just proved that in the previous question. We saw that D3 was equals to T3 because of exterior angle of a cyclic chord. And now let's look for the ones which we can use here. Let's check for F and F. So the F in TFO is this one, F2. We can prove that F2 is equals to F4. So then how can we prove that? Good question. So I want you to notice something, right? I didn't see this when we were doing the thing in the given statement, but this is also a radius. Like OF, it's a radius, right? And that means it's equals to OC. And then because OF is equals to OC, what you're going to get is that this F2, which is written here, is going to be equals to that C2. And you know that that C2, which is over there, is going to be equals to that F4. And then that means that F4 must be equals to F2. And just like that, you're done with your similarity, because you only need two angles, and then the third angle is just going to be obvious. So now what we're just going to do, we're just going to set out a statement to show that F2 is equals to F4. So what we're going to say is that OF equals to OC, because they are a D. And then what you're going to say F2 equals to angle C2. Why? Because they are angles which are opposite equal sides. And then now what you're going to say your F2 is equals to your F4, is equals to your angle C2. Why? Because of the tan chord theorem. And then now, therefore, your angle F2 is going to be equals to angle F4. Why? Because they are both equals to angle C2. So then now we can start to set out our statement for proving similarity. We're going to say in those triangles which are stipulated over there, TFO and triangle DFE. We already know that in triangle TFO, we have T3 equals to D3, right? So angle T3, and make sure that the side which you are writing, like you see the angle here, T3, it corresponds to the triangle above. So T3 corresponds to my triangle TFO. So that's what I'm saying, that you must make sure that the angle which you write on the left hand side corresponds to the triangle on the left hand side. It's just a matter of, I don't know, just being neat to some extent. And then so now we're going to say T3 is equals to angle D3. And we've proven this, right? But then we can just still write the same reason. Exterior angle of a cyclic chord, like as we have written in that previous question over there. And then I continue, and then now I write the ones which I just proved. I proved that F2 equals to F4. So F2 comes from triangle TFO, and F4 comes from triangle DFE. So now what I'm going to do is that I'm going to say my F2 is equals to my angle F4, and I'm just going to write proven. Proven above, okay? And then, which must mean that our third angle must be obvious. So the last angle which is left out, it's O, and the last angle over there, it's E. So what we're going to say, you're going to say that O in TFO, so it's TFO, so that's O2. Angle O2 is going to be equals to the last angle in triangle DFE, that E over there, angle E. And that's our reason. Our reason is going to be third angle of a triangle. And then this must imply that, therefore, triangle, we just write it as it was given. You see a given triangle TFO, given triangle TFE. We just write it as it was given. We're going to say, therefore, triangle TFO is similar to triangle DFE. And what's our reason? Because it's angle, 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 like that. So now we continue. They say that if B2 equals to E, so we're given that B2, let me just tidy up here a bit. So if B2 is equals to angle E, and then we're supposed to show that DB is equals to, is parallel to EA. Alright? So then now, how are we going to do this? So I also am just thinking about this. Wait, give me time to think about it. Oh yes, okay, I found it. So now what you're gonna see is that your B2 here is equals to your D1, right? Because if you check this triangle, we have this side equals to this side. So that means that D1 is equals to B2. And if D1 is equals to B2 and B2 is equals to E, that must mean that D1 is equals to angle E. And if D1 is equals to angle E, because they form like this F shape over here, that means that DB is going to be parallel to AE. Right. 10.4. What you're going to write is that B2 equals to angle E. This is given. And what we're going to write is that OD equals to OB, because they are radiuses or radii. And then what you're gonna say your B2 is equals to your D1. So it's this B2 equals this D1. So this must imply that angle E equals to angle D1. And if angle E is equals to angle D1, therefore DB is parallel to EA. And what's the reason? The reason is going to be corresponding angles equal, because this D1 and E are called corresponding angles. I know this thing is like a bit clustered here. Let me just try to clear up everything. Let me try again. Yes. Yeah, let me put it over there. And then so now we're doing 10.5. We are supposed to prove that DO equals to TO times FE over AB. So guys, these questions are usually the same sort of questions. So now here, we just proved that lines are parallel. You use what you have already used above. We just proved that these two lines are parallel. And then when you think about parallel lines, which theorem comes to mind? You think of proportionality theorem, right? Okay, that's good. So now what does proportionality theorem tell us to do? It's going to tell you that the most basic of proportionality theorem is that you're going to have OD over DE being equals to OB over AB. So you will have something like, I'm just doing this as a rough sketch, OD over DE being equals to OB over, let's just say AB over BA. And then so now here, you find that your OD is equals to OB times DE over AB. That's if I multiply by DE on both sides, because here it's going to cancel, and here because it's over 1, it's going to multiply with OB, then it's going to give us OB times DE over AB. I did this so as to show you that this is the same thing as this, but then here you have DO, yes, it's OD, and you have your AB here. But then what you have is that you have OB times DE, which is not the same thing as TO times FE. But then we can solve this issue is that when you do this similarity, these questions, you must use each and every single bit of information which you have ever found. So now remember in 10.3 we proved that triangle TFO was similar to triangle DFE, right? So now what that shows us is that if I have triangle TFO being similar to triangle DFE, therefore my TF over my DF is equals to my FO over my FE, and this is going to be equals to my TO over my DE, right? And then now you look for the sides which are familiar. So now look here, you have TO here on this one, and then you have FE here on this one, which is this, right? So then what does that tell us? That it tells us that therefore FO over FE is equals to TO over DE, right? And then now if you continue with this, you're gonna get FO times DE equals to FE times TO. And how do I get that? You just cross multiply. And then now, like, if you look at this, did I do this properly? Oh yes, I did. Oh yes, I did. Okay, now here you have FE times TO, which is the one over there in the proof. And then here you have FO times DE. But then here you have OB, and here you have OF. Then what do you do now? You see that, go to your diagram, you see that OB is equals to FO. Why? Because they are both radiuses, right? So then that means that here on your OF, you're going to have OB times DE equals to FE times TO. And because OB times DE is equals to FE times TO, that means that over there, you can replace it. Then you're going to get that you're therefore OD is going to be equals to FE times TO over AB. Like that. And that was the thinking process. But then now we are going to have to put it into writing. So now, what do you do when we put it in writing? That's because that's the most important thing, right? So now let's just put it clearly into writing. You got the general idea of what you're going to be doing. So now we're going to say OD over DE. So it's this OD over this DE is equals to OB over AB. And what's the reason? You can say prop theorem if you want. Yeah, let's just say prop theorem. And we state the parallel lines, DB parallel to EA. Yes. And then you're going to get that therefore OD is equals to OB times DE over AB. And then now remember, we can now just do the same time, because you know that eventually you're gonna replace. Let's just keep it like this. Then we'll do it later. Let's just keep it like that. So it's DO equals to OB times DE over AB. Okay, and then we go to our similarity, which we have in those two triangles. TF over DF is equals to FO over FE is equals to TO over DE. You remember this? I'm just taking it from these triangles which I see over there. So now, what's the reason here? I say similar triangles. And then from these three, I take the two which are most appropriate to what I want to prove. So which just so happens to be these two, like here. So I just say, therefore, FO over FE is equals to TO over DE. And if I cross multiply, gonna get therefore FO times DE is equals to FE times TO. And then remember, we said that this FO is equals to this OB. So we just write that, we just indicate that FO equals to OB. And why? Because they are both radii. Right. And then therefore, we can see that OB times DE equals to FE times TO, right? And then now with this and that, we can now conclude that DO is going to be equals to FE times TO over AB. And the reason being that our OB times DE is equals to FE times TO. And we are done. So thanks for watching, guys. If you have any questions, don't be too afraid to ask. Just ask ahead and I shall reply to you. Sharp.